So we're continuing our conversation surrounding controller design, process controller design. And what we have here is we have a transfer function for our process where we have four individual first order processes that combine to give us an overall fourth order transfer function with a overall gain of 1.5. So what ends up happening here is that in our previous, I could pull it up. In our previous conversation where we used the Ziegler-Nichols method to produce these two tuning values, our Kc and our tau I, we used a third order process that had not a controller gain, but a process gain over tau s plus 1 to the third power. So this assumes that we just have our third order transfer function as a function of our controller and our process. What we're assuming here is that now we have four individual processes that combine to give us this overall transfer function. So the first thing that I'm going to do is I'm actually just going to plot this out for, I think I can just copy this here, right? Yeah. So I'm going to put this out for a single unit step change. So that will be for our S here. So this is just a single step change. For our process, let's say I want 30 points. 30 points. Space 1.5 seconds away from each other. Seconds, hours, some time unit. Right? So now I'm going to go ahead. I'm going to go make subplots. Basically just that. AI finished it for me. That'll work fine. So let's go ahead and run this. And you see we get this nice smooth curve that gives us the value of our transfer function over a 30, or rather it gives us 30 points separated 1.5 units away from each other. Now, we also kind of want to give this a little bit of noise. Let me just change this to markers real quick. And I'm just going to simulate maybe what we have as an experimental set of data. So in order to do that, so let's say that we have some y. So the proper function for this, we're going to go to numpy.random.normal. And we're going to give it our location. And that's just going to be our h plot. And that's basically where it's going to randomize around. And we also want to give it the scale, so how much it'll deviate from. So we'll give the scale value of, let's say, 0.01. Then I'll change my y, so y equals y, match that up. And now we see that we have created something more of a real-life scenario where we have subtle shifts from the perfect curve that we had just plotting out the original transfer function that we were given for this problem. So this list is a list of Laplace transforms. And what I want to focus on here is this, focus on this number 13 Laplace transform here. So what we actually end up seeing is that we have what is essentially a first order transfer function listed on this side. We have 1 over s ts plus 1, or tau s plus 1 rather, and doing the inverse Laplace of that will give us 1 minus e to the minus t over tau. So this essentially can be used as a model to our to this curve that we have. So first things first, we need to define, we need a k, a tau, and a theta, right? So we'll say k is equal to 1, and say tau equal to, say, like 12. And then we also need a theta, say that's 1. So now we have a y model. And so that transfer function is going to look like k times, where is it? So 1 minus exp minus theta over tau. So minus theta over tau. All right. So this now, let's redo this plot. And we'll also add a y model. Okay, so I actually did end up changing this k and this theta to more reasonable values. But the actual issue is that this wasn't supposed to be theta. This is your plotting t that we pull from this simulation function here. And now when we do that, we find that we get this curve that almost resembles the shape of our plotted data. However, we see that we almost kind of want to shift our model over to where our theta isn't less than our, or where our t isn't less than our theta. So over here, we can give something like this, kind of a conditional where if we have our t is less than theta, then let's say our y is equal to 0. Otherwise, y is equal to that. Right. So now we see that this kind of lines up a bit more naturally. So we're starting here, less than 0, and then we set this theta value to where we begin seeing our curve up in our model. So this is how we give ourselves that little bit of time delay, which is where the name first order plus time delay, that model idea that we see here. So this is a first order plus time delay model, and these are some parameters that we'll be using. So it's based off of a time-weighted absolute error, and we use a theta and a tau in order to pull these values for our model. So in order to make the fit a little bit better, I can make another change, and that's basically saying that once we start actually plotting our values, we're going to shift it by our theta, our time delay here. Right? And now we can kind of mess with the theta and the tau as we see fit. So maybe we can increase our time delay, say for, yeah, that's starting to look a little bit better. And then maybe our tau is too big. So maybe let's set that to 8. And just by adjusting a couple of those values, we see that we get actually a much better fit for this model using the first order plus time delay. I'm going to implement a function to find a fit for our model using the sum of squared errors. So I'll do a new function here. So we'll say sum square error, something like that. And essentially what we're going to be taking in as inputs is I'm going to give it some vector v. So I'm going to return this vector, and the vectors that the pieces that we're going to return are going to be our k, our tau, and our theta, right? So we have our process gain, we have the time constant for our process, and we also have our theta, the time delay. and those are going to be what we unpack from our vector. Now we want to calculate the model using our calculation here, and I'm just going to pull that from here. So that's easy enough. And then what we want to return is exactly what it sounds like. It's going to be the sum of the squared errors. So NP sum y minus y model squared. So that's perfect, actually. So this y, remember, is our randomized plot that we have according to our transfer function that was given to us as part of the problem. And our y model is going to be based off of the vectors that we give it almost as an initial guess. So now that that function, so I just had to clear the runtime and run it all over again. So now everything should be fine. So now we have our function, and what I want to do really quickly is I just want to run this sum squared error operation, right? So sum squared error, and I'm going to give it our kind of initial guesses, you could almost say. So we have k tau theta. Well, I wonder why that is. Well, what if I'm just going to ignore that for right now, and I'm just going to try and see what happens if we try and run the optimize function on this, right? So CSP, so that's our SciPy library, to optimize dot root. So we're going to do our root solver here. So the function that we want to get our roots of is going to be our sum square error, and we're going to give it our initial parameters, so that's k tau theta. And now, hopefully, if we run this, so actually I used the wrong function here. It's not the root solver, but what we want to do is we want to minimize the sum of our squared errors. So we're going to use our minimize function here. And now if I hit shift enter, this X array gives us the values of k, tau, and theta that allows for the least amount of error within our model, the fit of our model rather. So what I'm going to do is I'm going to store these values into our k from our fit, our tau from our fit, and our theta from our fit. And we just want to pull the x attribute, so we're just going to hit .x. So now if we go ahead, if you want to go see what our k fit is, right, it'll pull us just the value from our array there. So now over here, instead of having the y model, that's not really defined anymore. So what I'm going to do is I'm just going to copy and paste this part here. Okay. And now for k, instead of k, we're going to use k fit. The t plot is still fine. This theta will be theta fit. This tau will be tau fit. So now this is the model that we derived from a nonlinear regression using the method for sum of squared errors. And you can see that it's already giving us a lot nicer of a fit between the data set that we have and the model that we just coded out. Now what we can do is we can move on to using some PID parameters using the Smith and Corripio relationships. So that is where we'll be headed next. So now these values that I have pulled here actually come from our set point for a proportional integral controller. So we have a proportional mode here and an integral mode here. So I've labeled this PA, PB, this is IA, and IB. Now what we see is that for our proportional mode, we have this relationship y equals A times our dead time over our time constant for the process to the B power. So that is pretty easy to code out. So we'll say something like capital Y. Gonna have to go back. So it's gonna be our PA times our theta fit over our tau fit. And this is going to be to our PB power. Right. Now, also, from this, we can now pull our controller gain by dividing our Y by our process gain K. So now we have our KC is equal to our Y divided by our K, which is going to be our K fit actually. Moving along. So now we can look at our integral controller here. We have this relationship that says our time constant, our tau, over our tau I, which is our reset time for the integral controller, is equal to the integral A. So instead of now using our proportional, we're using our integral mode. So that's going to be our A plus B times our theta over our tau. So now we just want to find this reset time here. So what we can do is we will move this tau over to this side, and this will be our tau fit. Hold on. So let's just do this. So tau I is going to be our tau fit divided by our integral A plus B times our theta, or sorry, our integral B, not just B, but integral B, theta fit divided by tau fit. And this should give us pretty much all we need to go ahead and actually simulate this like we have simulated earlier. So the three things that we still need rather, is we need to define our controller transfer function, our process transfer function, which we have actually, and then the closed loop. So this GC and this GCL actually follow very, very closely. It's the same relationship. Okay. And now, honestly, I think I'm probably just going to yeah, I think they can go ahead and take this as well. Let's just say T and Y. I'm gonna try and avoid confusion here. It's gonna be for that. Right. So now, well, that's not what I was expecting there. Okay, I accidentally had this set to just T-plot, and if you do that, it just doesn't give you what you need. So remember to change that to T. And now we have this is our closed loop simulation according to the Smith-Corripio parameters that we pulled. So the next thing we can do is actually we can do a Bode frequency analysis on this too. Here we go. And if we go ahead and we do that, we can find our crossover frequency. So let's find that. That's around a 0.28, I'll say 0.2829. We pull that here. We see that our amplitude ratio is around 0.4, 0.41. So that makes sense. We see that our closed loop simulation does eventually come to about a steady state centering at around 1. And that is how you can use both a nonlinear regression using a first order plus time delay model, as well as using Smith-Corripio parameters for a proportional integral controller, and simulate the closed loop of a fourth order transfer function. So going back through the code, I realized that there was a couple places where I didn't use the tau fit or the theta fit, instead just using the old tau or theta. So make sure going back that you are using those fitted parameters and not using the original guess parameters, because you will get a wrong answer. As you can see, we still have a stable closed loop simulation, but you will find that your amplitude ratio at the crossover frequency, which is about 0.31, if we find that here, your amplitude ratio is going to be about 0.33. So making sure that you are going through and you are double checking your work as you go along.